Today I'm just going to talk about some complex analysis in hyperbolic geometry and really the motivation of talking about these things, just to get people interested. These are some of these are new developments, either that or they're very niche and you don't have a lot of people looking at them. But they could potentially have some interesting applications. Hyperbolic geometry is used to get a lot of fixed point theorems in complex analysis. At the end, I'll show you some references you can look up and see all the ones that there are. Because there's a big sort of area of study, being the study of analytic functions on the ball, and a lot of people study under what conditions do these analytic functions have a fixed point, and can we make those conditions as loose as possible? There's that for fixed points, and also interpolation is a big one. So under what conditions, given a pair of points, can we guarantee the existence of, can we guarantee the existence of an analytic self-map of the unit ball that interpolates through given points? So, and that is sort of, that draws a lot from this theory of hyperbolic geometry. And what we're going to do today is just cover some basic facts about it. We're not going to really look at any huge results. I'm going to show you how to prove that the sectional curvature of hyperbolic space is -1. That'll perhaps be the biggest thing we look at today. And then I want to switch over to a topic that's of interest in dynamical systems, and low-dimensional topology. This is something called Anosov flows. And I want to cover them because there are a lot of open problems as it relates to them. And some low-dimensional topologists recently have used Anosov flows in their work. And I think that is quite interesting. So I just want to share that with you. So we're going to talk about the hyperbolic plane, what that is, get some nice visuals, and get comfortable working with non-flat space today. So throughout this section, delta is just going to be the open unit disk in the complex plane, and then the boundary, of course, is defined like that. And then we're going to define this group of conformal automorphisms. So if you haven't taken complex analysis, that's okay. Just think of a very nice map on the disk geometrically. If you have taken complex analysis, you know that by conformal means it preserves angles. Okay, so if you imagine two curves intersecting each other in the ball, and if you look at the point of intersection and draw the tangent lines for each of those curves, maybe a visual would actually be really nice for that. So if we're in the ball, and I have two curves. Here's curve 1. I'll just call that C1. And then here's curve 2. We'll call that C2. I can draw the tangent lines. So we'll just call that T1 for C1, and then T2 for C2. These make an angle. And what a conformal map does is, let's say these two functions live on the circle. Well, this is homeomorphic to the circle, so that's okay. So we have this self-map. This map, we can apply this map. We'll just call this conformal map. What would be we'll just say chi for conformal. It's a self-map from the disk to itself. We can compose chi with C1 and compose chi with C2. This will give us two new curves. But if chi is a conformal map, this angle here will be the same after the mapping. So these curves are going to shift around after I apply chi to them. But because chi is conformal, even though they shift around, this angle here is preserved. It's the same. It doesn't change. Okay. But we're not really going to worry too much about that. So if that's kind of a hairy idea, it's no problem. Okay. So one thing that's really important that we talk about a new sort of space, a lot of us here know topology, some of us do geometry, is looking at this as a metric space. It gives us an intuitive idea for how it actually looks. And how we are going to define this metric is a little bit different. So the standard Euclidean metric, the absolute value of the distance between 2 points, that's usually just given to you in your class in topology or metric space theory. But how we're going to get this metric is sort of curve minimization method. Okay, so we're going to look at all paths between these 2 points in this hyperbolic space, which we're going to look at, and then we're going to look at the shortest one, and we're going to gauge shortness by giving this space a metric. Okay, so but before any of that, just some basic facts. So a Mobius transformation, or a conformal map, well, it's a type of conformal map. It's just a complex valued function of this form. Okay, so we have AZ plus the conjugate of C, and then CZ plus the conjugate of A. It's very important that these coefficients are like this. This is how we get some big results. And these coefficients A and C satisfy this relation. Okay, and I think you guys can see my mouse good. And so the first big result with this, and this will be very important. This is called the Schwarz-Pick lemma. This is something that would usually be covered in a graduate course on complex analysis, but I'll show you some resources. You can look at the proof later. And this is usually an inequality, but since we're working with Mobius transformations, this is an inequality. And all it is, it's just this identity. We can write the derivative of the Mobius transformation in terms of the original function itself. Okay, so we have this relation between our original function g and its derivative that's explicit. Well, the modulus at least. Okay, so and the proof for that's quite simple. It's just algebraic. What I'm going to do, all you do to prove this, and if you're interested in this kind of stuff, I'd encourage you to do it. All we're going to do, we're going to evaluate the right-hand side and then compare it to the left. So all I do is simplify this, do a bunch of distributions. I will apply this identity that is essential to this, and I get the form of the modulus of the derivative of g. Okay, so that gives us the, and I'm going to, again, you will all have this PDF if you want to walk through the details, but it's an algebraic proof. Nothing too fancy today. So with that identity in mind, we'll just call it the Schwarz-Pick identity. What we have next is the hyperbolic metric. Okay, and it's going to be defined this way. You're going to see later why we put it 2 here. That's really for normalization. So we get a nice number when we compute the curvature, and it's just given by this. And you're like, okay, well, you didn't explain what a metric is. Okay, so you might be kind of lost. Don't worry about that. You're going to see what I mean later. And this is invariant by virtue of the Schwarz-Pick lemma. Okay, so what that means is if I compose lambda with a Mobius transformation and multiply it by the modulus of that derivative, I get lambda back of z. Okay, so this thing is invariant under Mobius transformations, and this is very important because if you think about it conceptually, if what I'm giving you, like based off what you already know about metric spaces, if what I'm giving you, I'm telling you is a metric, then then that metric should be invariant under extremely nice transformations of the space we're talking about. And in our case, the extremely nice transformations of the space we're talking about are Mobius transformations. Okay, they're great. All right, so we have this metric, and it is invariant under these Mobius transformations. Very important. Okay, and what we're going to find out later is that this metric space we're going to define, these Mobius transformations are isometries of them. Okay, this makes some proofs extremely easy. So, but now we can define the metric on this space. Okay, so if we have a curve, just a regular curve, from some interval on the real line to the complex disk, and it's smooth in the usual sense, then we're going to define the hyperbolic length of gamma via this integration here. Now, I don't know how many of you are comfortable with this kind of notation. So you see, well, we have dz here, and we have a modulus over it. And usually when you see dz, people will tend to leave it alone. They don't put a bunch of stuff with it, okay? Because you would think, okay, dz means take the integral with respect to z. Well, now you have an absolute value over it. And if you feel uncomfortable with that, that's okay. You're going to see how that works when we integrate later. Okay. And then we have the hyperbolic metric. If I have 2 points in my disk, the hyperbolic metric, the distance between those 2 points, is the shortest with respect to the hyperbolic length, the shortest path connecting them. Okay, so if you want to think about, okay, well, this definition's a little bit weird. Well, just think about Euclidean space. The shortest path between 2 points. We can define the distance between 2 points in Euclidean space to be the shortest path with respect to the Euclidean length, okay, between 2 points. And that's just going to be a line. That just comes from the triangle inequality, okay? This is the same thing, okay? But this time the shortest path between these 2 points looks quite different than a straight line because we're in hyperbolic space. And you're going to get a better feel. I'll show you some pictures later on what that, how that's going to behave, the length of the path, etc. Okay, and like I said before, this Schwarz-Pick identity is very important. We get this invariance under Mobius transformation. So if I transform a curve in the disk under a Mobius transformation, then the length of that resultant curve will stay the same. Okay, but I want to walk through this proof so you get comfortable with this integral notation, because I don't know how many of you have worked with something like this. It can be quite confusing when you see it for the first time. So we're just going to write the definition in this first line here. Okay, so we have the integral over g composed with gamma of lambda z with respect to modulus dz. Okay, well, when we do line integrals, okay, so remember how you do line integrals. So your basic line integral, I'll pull this up. We'll go over here. If we're just in, I don't know, we'll just r to r, or whatever. My integral, where's my cursor? Here, over some curve gamma of some function f of x dx. All we're going to do to evaluate that, we're going to have the integral from t equals 0, or we'll just say t equals a to make it more general, t equals b, of f of gamma of t. Sorry for my handwriting, by the way. I got a new tablet. It's terrible. I'm going to get a new one. Times the time derivative of gamma, and I take that integral with respect to t. Okay, so that's your definition of the line integral. And we do the exact same process, okay? So we're going to take, okay, well, here's the function inside the integral. To do the line integral, I'm going to do lambda of whatever parametrized curve is in here. So lambda g composed with gamma. And then I'm going to multiply by the derivative. What's my derivative with respect to? Well, gamma depends on z. Okay, so I'm going to be looking at the derivative of g composed with gamma with respect to z. Why? And that's where the absolute value comes into play. Okay, the reason, you saw in this case, I didn't take the absolute value of, where's my cursor right here? I didn't take the absolute value of gamma prime. But because I have absolute values around my differential, this tells me that I'm going to, and you can verify this using the fundamental theorem of calculus. If you go on Wikipedia, there's an explanation for the formula for line integrals. Okay, and if you replace dx with absolute value of dx and go through that same proof, you're going to see why. Now I'm going to be multiplying by the absolute value of the derivative here. Okay, now to evaluate this, I'm going to use the chain rule. I'm going to get some nice stuff that cancels out. And you can walk, this is really an exercise for you to walk through the intermediate steps between these two. Okay, but all it is the chain rule. And then now I use the invariance of lambda, that identity that we saw up there. Okay, so we have something that looks very nice and familiar here. And I replace that with, well, this right here is just the definition of the line integral, right? We have the function composed with the curve times the derivative of that curve. Okay, and that's just the line integral over gamma. Okay, so the line integral over a Mobius function, Mobius transformation composed with a curve, is equal to just the length of that curve itself. Okay, so we have this invariance of the hyperbolic length. This is important because once we have this, okay, you can easily see, since we define the hyperbolic metric as the infimum of the length of these curves, that it's going to be invariant under Mobius transformations, which means if I take a Mobius transformation G, transform 2 points, it's distance preserving. Okay, and so by virtue of that, we get an isometry. Does A and B not change with G? So A and B is gamma is defined on A and B, so the domain of G composed with gamma is still going to be that interval. Okay. I hope that answers your question. But we have this distance preserving quality of the Mobius transformations. It isn't, and I'll get to your questions in a moment. But anyway, so we have this distance preserving transformation, which is great. Okay, so we've defined a pretty nice metric on hyperbolic space. Okay, and again, this means conformal automorphisms of the disk are isometries of this metric space. This is going to be very important in talking about the topology of this metric space in a moment. And one fact that we can prove just using the fact that we now have isometries, we can actually derive, because this is kind of ambiguous, okay, what this is. We can actually just write an explicit formula using the fact that Mobius transformations here are isometries, okay? And we want to prove this explicit formula. The distance from the origin to any point z is given by this expression here as logarithmic. And this is important. You're going to see this visually as well, that the distance, as you go further from the origin in hyperbolic space, the distance follows this value. Okay, so I'm going to consider z as just its polar expression re to the I theta. I'm going to have this conformal automorphism that just rotates z to its, because if you look at complex numbers, the complex plane is just a series of concentric circles. I'm going to take z and I'm going to rotate it until it points until it's lined up with the real axis. Okay, so all I do is apply this. This is a conformal map. Okay, I take any w and I map it to w e to the negative I theta. Okay, so if I plug in z to this function, I'm going to get r times e to the I theta times e to the negative I theta. Okay, that's just going to be r times e to the 0, which is r. Okay, but this is a conformal automorphism. It's going to be an isometry. Okay, which is great. So it's going to suffice to prove this formula on the real axis for x between 0 and 1, between 0 and 1 since we're in the disk. Okay, so given any curve starting at 0 and ending at x, I'm going to write the curve in terms of its real and complex parts, and I'm going to evaluate the length. Okay, so again, some more practice with this. The length of any curve, okay, alpha t plus I beta t. If I plug in here gamma, so absolute value of d gamma, what am I going to get? Well, I'm going to get the square root. I'm going to get the modulus of gamma. So I'm going to get the square root of its real part squared plus its imaginary part squared. Okay, and this 2 times and over this, well, that's the function lambda. So here we have gamma plugged into dz, and then here we have gamma plugged into lambda. So I have this integral. And this is just algebra. That's greater than this integral over here, which is greater than this one. And finally, we have that it's greater than this integral right here, which is computable explicitly, and is in fact what we want, which is log of 1 plus x over 1 minus x. Okay. Equality is going to hold here, so we're going to get equality when alpha dot, okay, the time derivative of alpha, the real part of gamma, is greater than 0, and beta is equal to 0, the imaginary part. And that makes sense conceptually. Okay, if I'm looking at a curve joining the origin with something on the x-axis, you want it to stay on the x-axis. Okay, so you get this equality here. Now, so this proves this result. Now, what's really nice about it is that it tells us a couple things about this how this hyperbolic distance works. Okay, first thing, if we want to prove it's a metric, okay, this goes into proving it's a metric. I don't state the theorem. We're not going to show the full proof it's a metric. These results all show it. But if z is non-zero, then obviously this is going to be positive. Okay, so that's one. But the second one, which is going to give us lend to some geometrical intuition, is that this, the distance between the origin and a point in a hyperbolic plane blows up as z approaches the boundary of the disk. Now this actually makes sense with a lot of the pictures you've probably seen online, and we'll take a look at them. So there are different ways of looking at hyperbolic space, but I'll just I'll show you a couple here. This guy Code Parade, he made this video on non-Euclidean geometry. It's pretty good. But anyway, so we have these two. There's different ways of visualizing hyperbolic space. You use these different projections. I'm not going to go into it. But I want to show you how you can see that if I start at the origin and I move to the boundary of the disk, the value of the distance blows up to infinity. Okay, I want to show you why, like visually, how you can see that. We'll say that the center of this box, I'd rather this be spherical, but that's okay. The center of this box, well, let's go with the stereographic projection. I'm shading around here, but the center of this circle here, this is the disk. Okay, just say this is the disk, the complex disk, okay, the unit circle. And here we go out towards the boundary. We start at the center here, so this is 0. And if we move towards the edge, okay, these points here in the distance, the smaller they are, the further away. And you can think of that as you're at the top of this mountain, okay, and it's tiled with these square tiles. They're kind of warped. And you're looking off in the distance, and of course if you look off into the distance, the tiles are going to appear smaller, so they're going to be further away. And you can see that here. And look how fast they get small. Okay, and you can see if you play the video, if I'm walking down the mountain towards the bottom, okay, the tiles that were further away get bigger, but you still have these really small tiles off in the distance. They're still super far away. And so as I travel, if I want to reach those tiles that are super small, my distance from the origin is going to blow up. It's going to increase very quickly. Okay. So that gives you some intuition geometrically for this. Okay. And we have this nice identity. There's a lot of identities like this that you can have, and they're very useful in geometric function theory. But if I take the hyperbolic cosine of the distance from 0 to some point in the disk, I get a nice identity here. That's about it. You just get this is just a nice identity. I thought I'd share with you today. But the fact that we've proved we can get an explicit formula from 0 to a point z, this allows us, using the fact again that our conformal maps are isometries, that we can get an explicit formula for the distance between any 2 points. And it's given here. All we do with this, how do we do this? We just get a conformal automorphism that swaps w with the origin. Okay, and this is conformal since my distance map rho is preserved. The distance is preserved under conformal automorphisms. I can apply this origin swapping automorphism to each of these entries. Because we're swapping w in the origin, this goes to 0. I just switched the entries to mess with you. And then we use the explicit formula from up here, and we get an explicit formula for the hyperbolic metric. So that's great, because now we don't have such an ambiguous definition, being the infimum of lengths of curves. Okay, so that concludes that section. The next section, I want to actually start computing lengths of just simple geometric shapes. And the first one that would come to mind naturally would be the circle. Okay, so what does a circle look like? And what is it like in hyperbolic space? Okay. Now it actually turns out that every Euclidean circle is a hyperbolic circle. And every hyperbolic circle is a Euclidean circle. Okay. And we know that, okay, if I have a Euclidean circle Z centered at the origin, okay, that's just this set. Then if I transform this set, if I look at any Z and C, and I look at the hyperbolic metric applied to a point on a Euclidean circle, then it is always equal to this. This is the fixed value. Okay, so we get log by our explicit formula of 1 plus the modulus of z over 1 minus the modulus of z, but z lives on the boundary, so its modulus is always fixed for every z on the boundary. So we have this fixed value here. So we can write C as a hyperbolic circle centered at the hyperbolic origin with the hyperbolic radius r equal to log of this expression up here. Okay? So this circle here is equivalent to this one here. This is great. What this tells us, and we can apply this more generally, I'm going to skip this part. We do the same method as we did up here. We'll take this conformal automorphism, swap the origin, and move on from that. But the reason this is important, if the circles in Euclidean and hyperbolic space are the same, then their topologies are going to be the same. More formally, the class of hyperbolic circles on the disk is going to coincide with the class of Euclidean circles. The same thing holds true for disks. I think I just said that. And by virtue of that, open disks, by virtue of that, you have that the hyperbolic topology on delta is going to coincide with the Euclidean topology. Okay? So it's a comfortable space to work in. Okay? Nothing too bizarre when it comes to the topology on. Everyone's familiar. If you're familiar with the Euclidean topology, you can work with the hyperbolic topology, but we're not really going to do that today. Now, as far as the circumference, this is going to tell you about how this hyperbolic space behaves. So in hyperbolic space, we're going to get a different, well, we're going to get a different formula for the circumference of the hyperbolic circle. It's quite interesting. So as it turns out, if I have a hyperbolic circle in the hyperbolic plane, then the length of it, or the perimeter, or the circumference, is 2 pi times the hyperbolic sine of r. Okay? This is going to give us some important information. The reason we're computing this right now, this will tell us a lot about the geometry of the space, specifically the curvature. And you'll see how we can compute that in a moment. And to prove this is actually quite straightforward. We're going to get a conformal automorphism, and we're just going to apply it, okay, to the Euclidean disk so that it will transform into a hyperbolic, well, I say disk, circle. So it transforms to a hyperbolic circle. Okay? So we get a parametrization of C lended by just the standard parametrization of the circle here. The Euclidean circle, again, we're doing the Euclidean circle right now. We have that the length of the hyperbolic circle CR, we apply this conformal automorphism G, right? Length is going to be conformal automorphism invariant. So I say, okay, well, I can just compute the length of the Euclidean circle in hyperbolic space. And I just do just that, okay? So I have a line integral. I have my parametrization with respect to theta. Theta is my parameter. Here are the bounds on how theta changes. I do the same thing as earlier. I do a chain rule. I do some differentiation. Okay. I encourage you, if you want to walk. This is a very easy, it's just algebra and calculus. You've done this before without realizing it. And it just is a simple integral and computation. Okay. Now, one thing to note, this is where I said it's going to give you some intuition for the geometry of hyperbolic space. As r goes to infinity, my circumference grows exponentially. Now, this is compared to Euclidean space. Your circumference in Euclidean space grows linearly, since it's 2 pi r. In hyperbolic space, it's going to grow exponentially. Okay? So this, again, the circumference of a hyperbolic circle is going to grow faster than the Euclidean one, and this result establishes that. That's important, because now we can get a feel for the curvature of it. Now, computing the curvature is not necessarily always a straightforward process, but I looked around for the easiest way to show you that the curvature is -1. A lot of complex analysis texts will state this. So the sequel to all fours, which is conformal mappings, he asks you to prove the curvature is -1 for hyperbolic space. And a lot of the texts I'm reading now also discuss that as well. But I'm going to show you why that's the case. So there's this textbook, Riemannian Geometry. It's an old one, 2nd edition. And it says that the length function of hyperbolic circles admits an asymptotic expansion. If you haven't seen big O notation before, that's okay. It's going to be equivalent to this limit down here. But we want to solve for the curvature of the space because that's going to tell us how this hyperbolic space bends. It's going to give us a number to describe that. So just bear with me on this. So the function, the length function here, has this asymptotic expansion as r goes to 0. All that means is the limit of this expression, where k is what we're going to solve for, the sectional curvature is equal to 0. Now you can do this. This generalizes to any Riemannian manifold. Okay, so we're going to apply this general result to, in our case, the Riemannian manifold is this hyperbolic space, and the metric is the hyperbolic metric. And we have this result from general Riemannian geometry. We know this limit is 0, and we can solve directly for k. Okay, we know what the length of the hyperbolic circle is. That's just going to be its circumference. Okay, I plug that in, I do some algebra. You can fill in the intermediate steps, it's just algebra. And so I get this limit needs to be equal to 0 as per the theorem discussed in this textbook. Okay. All we have to do is we figure out the limit of these first two components. That's going to be 1/6. Okay, we need 1/6 plus k over 6 is equal to 0. We get k equals -1. And that's it. The curvature, the sectional curvature of hyperbolic space is -1. This is how you acquire it. This is a very nice formula, very, I would say, straightforward, easier way of doing it. It's just algebra in this case. Okay, so all you have to know. So this is also an important result because it tells us if we know what the circumference of our circle is in whatever space we're working on, then that will give us the sectional curvature. Okay, so how circles behave, how the perimeters of circles are in whatever space we're working on, in this case hyperbolic space, that gives us information about the curvature of the space. That's great. And in this case, it gives us the explicit sectional curvature, which is going to be -1. Okay, so that's the hyperbolic portion of today's talk. Some references you can look at. Here's what I would recommend. If you're interested in this kind of stuff, I would start with this book. This is the easiest book on the subject. So this is Composition Operators and Classical Function Theory. This is going to walk you through Mobius transformations. Okay. For some advanced, what we did earlier with Pick's theorem, that's some more advanced complex analysis. I would start with chapter 1 of this book to get comfortable with just the hyperbolic space and working with these integrals where you're taking the modulus of the differential, stuff like that. Okay. Get an, that helps you get a feel if you haven't been exposed to Riemannian geometry, which I'm assuming you guys have not, assuming anyone watching this has not. This is a good start, the first chapter of this. To get really deep into things like Pick's theorem, interpolation theorems, that's what this book covers. This is a very advanced book, though. You're going to need to know quite a bit of measure theory and, I would say, some functional analysis. Okay, this is a very, very hard book. But it has a lot of information. So like Pick's theorem comes from here. And some of this hyperbolic stuff too, but I think it's fleshed out more intuitively in this Bedford book. Okay, and this Riemannian geometry result comes from this book. I haven't read this book, but the result was discussed in that book, so that's why I'm referencing it. Okay, so I'll pause for a moment, see if you guys have any questions. So, okay, Nikolai asks, this exponent here, is at r to the n? So in general it is. The general result it is. In our case, since the tangent space is two-dimensional, okay, everything's squared. Okay. But the general result is going to be to the n. But in our case, it's 2. So I just simplified it. But in this book, on this page, they just square it. But in the next 20 pages, they state the general result with n. So good question. And another formula for computing it. Okay. Are the colored square tiles something like e-balls? I don't know. To my understanding, it's just a way to visualize, What are you trying to say? can show you this result right here. This is just from the textbook. So I have this, we have this asymptotic expansion, and then take this limit. What I just did, I just solved this for the sectional curvature K. Wikipedia has big O. I guess it just depends on who you ask. Oh yeah, I do have big O there, don't I? Any other questions before we move on? And Anosov flows is just going to be a few minutes. Oh, 3.98 states the more general result. I didn't change that. Let me... Yep. Oh, I see what you're saying. What's 2r for small r? 2 over. Trying to see what you're talking about. Two over 1 minus c. Oh, the metric. Right. No, I didn't really go into that. I just kind of said this is what we're going to define it as, and now the 2 is there as a normalization. If we didn't have the 2, then this would be different. But we have the 2 there in the numerator, so this is going to be so that's a nice -1. But if you do plug this into Desmos, kind of a rickety thing of doing it, you'll see that this limit is going to be 1/6, and then you solve for k. So this is in fact the limit, but we can always look at it later. We'll come back to it later. But now I'll just touch on Anosov flows. Let me just make sure there wasn't anything else. Yeah. And so here's this book. So okay. So I'm gonna jump gears. So if you had trouble with, this is going to be a bit of a disjoint subject. I want to talk about this idea of an Anosov flow. So you are all familiar with flows in general. If I take any vector field, okay, so if I'm at a river and I have a rubber ducky and I put it in the river, the trajectory of that's going to trace out a line. So that's an integral curve. You consider a lot of integral curves together, that's a flow. It's exactly what you would think it is, okay? It's exactly what you would think it is. That's not the rigorous definition, but that's how you can think of it. And an Anosov flow is quite interesting. It's very ambiguous. Any definition, if you go on Wikipedia, it's not a very concrete definition. What I just want to do here, the purpose of this part, is just to give you the intuition of an Anosov flow, because it is quite interesting. And it interacts in a... you'll see how the definition arises if we look at hyperbolic space. So this is a hyperbolic paraboloid. I'm going to try to task you with a visual exercise. If I take say, just a block of water above here, and it's just sitting there, and I release it, okay, not too fast, and it's going to land here on this saddle point, but again, it's a block of water. The water to the right over here is going to flow down towards the saddle point. But the water, we'll just say, going front to back, that's going to expand and flow down the sides like this. So what you can think of what's happening, say we're working with a compressible fluid. Maybe not water, we'll just say some of more viscous putty. You have, if I'm at this point right here, and I just think about the water in this neighborhood sitting on the surface, the water that's sliding down from the sides is compressing the water on the saddle point, or putty. I'll just say water, but it's really a thick water. But the water sliding down the sides is tugging on it. So we have a stretching in one direction and a squeezing in the other. Does everyone sort of see that? I hope that's clear. It's very important. So we're on this hyperbolic surface. We're imagining a fluid, and the reason this is also hard to conceptualize is because what I'm about to talk about only exists for 3 manifolds, which you can't visualize. Okay, so a 3 surface is a surface that's locally 3D. Okay, but you would immerse it in, what would that be? R7, right? 2n plus 1. So, or embed. So, the idea of an Anosov flow is to capture this idea. So we have this trajectory curve, okay, that moves along throughout space, and we have, and you can view that compression and the expansion as 2 forces acting on it. So I have a particle that moves through space, okay, for time t, okay. So it follows this trajectory, and as it follows this trajectory, 2 forces act on it. One that compresses it, we get this vector E minus that pushes inward on it, and we have this vector E plus that pushes out on it. And as time moves along, these vectors will change. And they do so exponentially. That's the idea of an Anosov flow. So if you want to think about an analogy that you know from physics, okay, we have 2 types of forces acting on this particle, or 2 types of vectors acting on this particle. If we go to physics, we can consider maybe a beam. I'm just sort of making something like this up, but we'll look at it like this. So we have this beam, and it's moving through a vector field where we have different, maybe it's moving faster over here, and maybe it's in a stream, and it's moving a little slower over here, and the vectors get larger, and etc. When this moves, you're going to have 2 forces acting on it. Okay. We'll say relative to this point A, okay, you have the forces acting on the beam, but a force applied, if I have a rigid body, okay, which means it doesn't bend, and I have forces applied at a distance from a point on the rigid body, it's going to generate something called a moment. Okay, it's going to cause it to twist and turn. I mean, that's what causes things to spin. So if I, we'll just ignore what's going on up here. If I apply a force F here, okay, that's going to cause a rotation. Even if I'm, even if this is moving, that's going to cause a rotation. Okay, and that's called the moment. And that's equal to, if I have the force F, that's going to be F times the distance from the point I'm talking about. Okay, that's going to generate a moment. Okay, so the point is, examples of things as they move throughout space. You have 2 types of vectors acting on it. Okay, because a moment is not a force, but it is indeed a vector. Okay, And I'm just trying to give you some physical intuition. This is a very, this is also why I'm talking about it today. This is a very ambiguous thing in the sense of we don't know, there are a lot of open problems about it. We don't know too much about the existence of Anosov flows. But anyway, we have this general idea. It's analogous to, you have a curve moving throughout space, you have its tangent line, you have the normal line, you have the binormal, okay? And you can view those as forces, okay? So, or vectors, excuse me, in terms of like kinematic vectors. So your tangent vector, what's that going to be? Well, that's going to be your velocity. Your normal vector could be something like centripetal force, okay? And then your binormal will be something different, okay? And what ends up happening sort of in a more rigorous manner, what we're doing is we have this tangent bundle of our whatever space, whatever of some three manifold, okay? And so this is 6-dimensional. Well, let's not talk about dimension. That might confuse everyone. And the idea is that we're able to break down at a point, okay? At a point, we're able to break it down into the direct sum of something like this, where we have some contraction. We also have this third component I didn't talk about. That just stays the same. So if you think about, you have a malleable ball moving through some vector field, and it's just heading in one direction. Okay, and that direction doesn't change. That's kind of what E0 is here. Okay, there's no these vectors are constant. Okay, but you have this squeezing force E, and you have this expansion force E plus. And the vectors, these vectors will grow and shrink exponentially as time goes on. So if I go along this parametric curve psi, this gray vector E naught is going to stay the same. But my contraction vector E minus is going to shrink exponentially. Okay, there's an explicit instruction on how that should shrink, and it is e to the negative t. Okay, and then our expansion vector, that's going to keep increasing exponentially as well. And all an Anosov flow is, it's a flow that can be broken down into these three components. Okay, something very interesting comes up in dynamics. So the book that had ergodic theory in it, okay, that also has dynamic stuff in it. So this comes up in the context of dynamics, and dynamics comes up in the context of low-dimensional topology. And so you'll see a lot of interesting research regarding Anosov flows in low-dimensional topology. But I wanted to, but that's it for today. All I wanted to do is sort of introduce this idea of an Anosov flow because I found it to be quite exciting. You know, looking at this very physical, what I think is a very physical interpretation, being an expansion force and a contraction force on a parametric curve. I find that to be quite interesting. So, but thank you all for listening. Depending on how much work I get done next week, this upcoming week, I'll probably look at presenting something a little bit more sophisticated and concrete, something along the lines of, well, we'll just have to see. But just a little taste of hyperbolic geometry and I guess what you would call some low-dimensional topology, this idea of an Anosov flow. And I didn't, you'll notice I didn't make any effort to define this thing rigorously, because it's very conceptual and very loose. You can define it rigorously, but it would take up way too much time for today. But anyway, thank you all very much for your attention. I'll be happy to take any of your questions. Maybe if they're on Anosov flows, won't be able to answer them too much right now, but maybe in the upcoming week. I have still a lot to learn about these things, but I just wanted to show you Very cool visual interpretation. So. R7. So the tangent, so you can, there's something called I believe it's the Whitney embedding theorem. Correct me if I'm wrong. So the Whitney, I'll just call it the Whitney embedding theorem. So an embedding is I can just, I can just visualize it in a given space. So like the unit circle can be embedded in R2. Okay, so very loosely, I can see the unit circle. Okay, not a projection of it, not a part of it. No, I can see the entire unit circle. Okay, so we say that we can embed the unit circle in R3. Generally, an n-dimensional surface can be embedded in R to the 2n plus 1. That's something called the Whitney embedding theorem. When I was talking about Anosov flows, the reason they're kind of difficult to wrap your head around is that they don't start existing. What we have here is at least a 6-dimensional tangent bundle. Okay, so if I have an n-dimensional surface, the tangent bundle is going to be twice that dimension. So if I have a 3-manifold, my tangent bundle for that will be 6-dimensional. Okay, so I need at least, right, if I'm going to break something up into the direct sum of 3 vector spaces, I need at least 3 dimensions. Okay. And so, but there's no manifold whose tangent bundle is going to give me there's no manifold who gives me a 3-dimensional tangent bundle, because your tangent bundle has even dimensions. So we can do, but it needs to be an even split on the direct sum. All of these need to be 1-dimensional. So we would need a 3-manifold. So that way our tangent bundle is 6-dimensional and we have an even split. We might say, okay, well, what about a 2-manifold? Because then we have a tangent bundle of 4. Doesn't that give us enough? Well, then it's not an even split up. Okay? Because 3 is not going to divide into 4. Okay. So the point I'm making with that is, do you see what I mean? So the manifolds that these are used for cannot be embedded in a space that we can see. Okay? So a 3-manifold, its tangent bundle is going to be 6-dimensional. Okay? The 3-manifold itself we can embed. We are guaranteed to be able to embed it in R to the 2 times 3 plus 1, so R7. I'm not going to worry about embedding the tangent bundle, but yeah. Hope that answers your question. Are there any other any other questions? Yeah, thank you. Good, very good question. Okay. Well, unless Tropy has a question. And as far as geometric measure theory goes, what we're going to do, I'll just give you an update on what that's going to entail. We're going to look at Thanksgiving or the start of winter break. I'm going to make a GitHub, and everything's going to be on there from the start. All of the homeworks for the entire thing. It's going to be about 7 weeks, 7 to 8 weeks, if we move at a pace of 2 lectures a week. And the lectures are already uploaded on YouTube. Okay, so what we're going to have for Saturdays is discussing the homework problems. And so we're going to look at the start of winter break, or we'll look at the start of Thanksgiving, and it'll be a nice, easy text. We're not going to read Federer. I think that's like reading Lang. That's actually worse than reading Lang. And then after that, or we'll just see how long it goes. We may not move at such a quick a pace, but that's the plan. So I'm going to make that GitHub, And once I do that, more details will follow specifically on when we'll start. It also depends on who we can get together to do geometric measure theory. But that being said, if we want to do a different subject, if I'd rather there be higher participation with an easier subject or a subject more people are interested in than have low participation with something, I just care about. Because a lot of people don't. It's a very small field. So, So there is this notion of a hyperbolic manifold, and I don't remember the definition. I would recommend the book that will give you information on that will be in the references here. You'll have the PDF. Oh, I didn't put it. That's terrible. It'll be a book. It's called Foundations of Hyperbolic Manifolds by Ratcliffe. Ratcliffe. And that'll talk about it. Anyway. So, and if you guys have, if we can get a lot of people together who are interested in studying a particular subject, please let me know. Be nice to get some more activity on here, though I know people are definitely busy. Nice. Thanks for posting. Okay. That's it. Thank you guys for your hour's worth of attention. I'll post this later. I'm going to have to cut it up, though.